So we continue our marathon today. And now it's turn by Alessandro, right?
Yes.
Do you hear me? So yeah, so recording is on and
Okay. So do you see my screen now?
Yes, it's fine.
Do you see also my pointer?
Sometimes, yes.
Okay. Okay, cool.
Okay, so let me first present you. So next talk is by Alessandro Giacchetto. And Alessandro will tell us about the multicurve count, Masur Veech volumes, and topological recursion.
Thanks, Leonia. So yeah, first of all, let me thank you, the organizers. Well, this is the first time for me at this conference. So it's a pleasure to also be able to talk. And yeah, I really hope to see you all next year in person. So today I'm going to talk about multicurve count, Masur Veech volumes, and topological recursion. And this is based on two joint works with Jon Andersen, Gaëtan Borot, Séverin Charbonnier, Vincent Delecroix, Daniel Lewansky, and Campbell Wheeler. So, so the general setup here, it's the same as the one of Jon's talk. So I will consider sigma to be a bordered surface. That for me, it's a smooth, connected, oriented, stable surface of a fixed genus G and with n labeled boundary components. So I can then consider the Teichmüller space, which for me, it's you can think of it as the space parameterizing hyperbolic metrics on sigma. With fixed boundary lengths, and you consider that up to isotopy. So this also comes with a natural symplectic form, that is the Weil-Petersson form, and this means in particular that I can integrate functions. So I will use a slightly different notation from the one used by Jon. So let me explain this in a moment. So I will talk about multicurves that for me are just a collection of simple closed curves, gamma I. They are all considered up to homotopy. And I consider them with multiplicity, mi, that are just positive integers. And I always suppose that these multicurves, they are not null homotopic, and they are not homotopic to boundary components of the surface. And I also consider them to be pairwise not homotopic. And I call a multicurve primitive if all the multiplicities are 1. So you can think of a multicurve as something like this on your surface. And the main point for me is that we can talk about length of multicurves with respect to a point on Teichmüller space. And I define the length of this multicurve as the sum of the length of each component multiplied by its multiplicity. So the main object I want to consider in this first part of the talk, it's the following counting function that was considered by Mirzakhani. So this is a function from the Teichmüller space cross R plus with values in the integers. And it's the function counting the number of multicurves with respect to the fixed hyperbolic metric of bounded length. So this T, that it's the element in R plus, is somehow the cutoff variable that it's that I will consider. So the first goal of the talk is to actually compute this function. So is there a way to compute this function as a function of sigma and T? And well, the second goal is to compute its average. So this function is invariant under the action of the mapping class group. So it descends to the moduli space, that is the quotient of the Teichmüller space by the mapping class group. I will denote it with just this G and N because it depends only on the genus and the number of boundary components of the surface. And I can integrate this function over the moduli space. So this geometrically is just the average number of multicurves on a surface of genus G with n boundary components of this fixed length L, whose length is bounded by T. So the second goal is to compute this function. So, okay, these are my two goals, but let's forget about this for a moment and let's see what we can do based on Yön's talk from yesterday. So Yön yesterday explained that using the geometric recursion and topological recursion from his work with Gaëtan and Nicolas, you can compute what I will call multiplicative statistics of primitive multicurves. So let me recall you what I mean by this. So first of all, let me fix a function that is decaying fast enough at infinity. And we can then consider the following function on the Teichmüller space that depends on this choice of f. And this is a sum over all primitive multicurves, so multicurves without multiplicity, if you want. And then you can take the product over all the components, and you take this function f that you fixed evaluated at this length. So if f is decaying fast enough, this function is actually well defined, and you can integrate it over the moduli space. So you can consider its average. And what Yön explained yesterday is that this function can be computed using geometric recursion, and its average can be computed by topological recursion. And also, well, he didn't explain this, but I will explain it now. You can also express this average as a sum over stable graphs. So the next 3 slides are just to recall these 3 facts. So yeah, this is just the definition of this function. And what I mean by what geometric recursion can do for you is to compute this recursively. So you have a Mirzaani type identity for this function, where you sum over these p's that are embedded pairs of pens in your surface sigma. And in the first sum, you sum over all embedded pairs of pens p of this form. So those are bounding the first boundary component of the surface, the mth one, when you where m is given by this sum. And then they bound a third curve inside the surface. And the second sum here with the C-type pairs of pens, they are pairs of pens of this type, where you bound the first boundary component here and 2 internal curves, gamma and gamma prime. And this is a recursion because you can see here that you then have to evaluate this function at sigma minus p. So removing the pair of pens, you reduce the other characteristic of this surface. And yes, for this C sum, you can either have the connected or disconnected case. But the main point is that here these functions B and C are very explicit functions. So for every choice of your f, the way you can construct these kernels is just by twisting these Mirzaani kernels with this function f in this explicit way. And this C Mirzaani McShane and B Mirzaani McShane, you saw them in Yön's talk like this, but they were also introduced in Paul's talk in this way. But the point for me is that they are very explicit. As soon as you fix f, you have this bf and cf. And so what you can do then is take this recursion and integrate it against the Val-Petersson volume form. And if you take this relation and you integrate it, you get a topological recursion relation for this average. And yeah, the main point to obtain this is actually the Wolpert formula for the Val-Petersson form. So I will not have time to explain this, but basically this dl, it's contributing with this integral and this dl here, and the tau is giving this multiplication by this small l here. But the point is that you have a recursion for these functions with some initial data. Another thing you can do is actually take omega f and take its definition and integrate it. So here, basically, you can either integrate this relation, or you can integrate directly the definition of omega. And if you do so, you get that the average of omega over the moduli space is given by a sum over stable graphs of this type. So here there's a lot of notation I will not be able to explain. If you don't know what a stable graph is, it's not important, but the main idea is that for every multicurve you have in the definition of omega, when you take the quotient by the mapping class group, the only things that will matter are somehow the components that you get when you cut the surface along these curves. And you can capture this in a stable graph where the vertices of the graphs are, they basically contain the genus of the components. So here in this case, you see here a component of genus 1 and 2 components of genus 0. And the internal edges corresponds to the components of the curve. So you can see here. And the boundary components of the surface are just the legs of the stable graphs. And what you have to do is just put the Weil-Petersson volumes on each vertex. And you put this function f on each edge, and you take this integral. So, so this is what we can do. So now let's go back to our original problem. So we would like to compute this function here, but actually what we can do using geometric recursion is compute these type of functions. So how can we use the right-hand side to compute the left-hand side? So there are actually two problems, but let me first rewrite the left-hand side in a way that it's somehow closer to the right-hand side. And so if I can write the left-hand side in this way using the Heaviside theta function. So h is the Heaviside theta function, and you can see that this counting here, it's basically just this sum. You sum over all multicurves, and then you take this indicator function that's Heaviside. And you can see that in this way they're kind of similar, but there are two main problems. So the first one is that the left-hand side treats the length of this multicurve in an additive way, because here the length is appearing as a sum of the components, while on the right-hand side I take the product of f evaluated at the length of these components. And the second problem is that on the left-hand side I sum over all multicurves, while on the right-hand side, I sum over just the primitive multicurves. So how can I solve these two problems? And this is actually kind of easy. So there are two main tricks. The first one is to take a Laplace transform. So I take this function, and I take the Laplace transform of it with respect to this cutoff variable. So remember that t, it's the bound you put on the length of your multicurve. So if I take this Laplace transform, you just have to know that the Laplace transform of the Heaviside, it's an exponential. So you get this formula here. And this is somehow solving the first problem, because you see that the exponential has this nice property that it transforms sums into products. So this is how I get this second equality. But still, we have just a sum over all multicurves here, and I want to reduce it to primitive multicurves. So the way I can do this is by summing over all primitive multicurves and then sum over all possible multiplicities. And if I do this, I get this third equality. And well, now I can just free sum this geometric series as soon as the real part of S is positive. And I get this function. So with these two tricks, the Laplace transform and choosing f to be this exponential decaying function, I can actually compute the left-hand side using geometric and topological recursion. So the punchline of this is that, well, after Laplace transform, we can compute the number of multicurves by geometric recursion, and we can compute its average using topological recursion. And we can also compute it using some overstable graphs. And this fact was actually known to Mirzakhani, was present there in one of their works. So let me just tell you that we can actually translate the topological recursion for this average number of multicurves in the Chekhov and Arthur Rantan form. And what you have to take, it's the data x and y as in the Mirzakhani's curve, the one computing Weil-Petersson volumes. And what you have to do is to modify B, the Bergman kernel, adding this sine 1 over sine squared behavior. And the precise relation between the two is that if you take basically the principal part of these differentials, you can get this average number of multicurves after Laplace transform in, well, the cutoff variable, the t, but also the boundary lengths. And yeah, just to show you what this means is that basically we can compute these functions explicitly using a recursion. So here it's just a couple of cases. Okay, so basically I already explained to you how to solve the two problems from my second slide. But what you should take from yesterday's talk of Yun is that geometric recursion is somehow more general, and I don't have to restrict myself to the Teichmüller space. So what I want to explain is how to do the same thing, but in another setting that I will call the combinatorial setting. So now what I want to do is completely change the spaces I have. So instead of taking the Teichmüller space, I will consider what I will call the combinatorial Teichmüller space. So instead of parametrizing hyperbolic metrics on sigma, I want to consider embedded metric ribbon graphs on sigma that are, again, are restricted to have boundary lengths that are given here. And I consider everything up to isotopy. So if you don't know what a ribbon graph is, it's not important. You can imagine to be just graphs embedded in a surface, and I want them to be, I want them to come with a metric. So this A, B, C, they are just positive real numbers. So the point is that this space, it comes with a natural symplectic form that it's called the Kontsevich symplectic form, and it's quotient by the mapping class group. It's called the combinatorial moduli space, which has a finite volume, and it's given by just psi classes intersection numbers. So this was well studied by Mumford, Thurston, Heider, Penner, many other people, and it was also used by Kontsevich in his proof of Witten's Witten conjecture. So yeah, when to go from the Teichmüller space to this moduli space, what you have to do is just forget the marking and you just get a metric ribbon graph. But the point of considering this Teichmüller space is that basically what you can do is to talk about the length of simple closed curves with respect to a point in this space. So the way you should think about this is that you are somehow considering some metrics that are very degenerate, and you have a metric just along the edges of this embedded graph. So if you have a curve, you can always homotope it to the graph and measure the length with respect to these edges. So this will somehow replace the concept of geodesic length in the hyperbolic case, and we can just consider this combinatorial setting. So what we were able to prove is that in this case, for every choice of Pence decomposition of your surface, there exists some length and twist coordinates that are Darboux for the Kontsevich form. And so this is a combinatorial version of this Wahlberg formula. And another thing we were able to prove is that there exists a combinatorial Mirzaani-McShane identity. So again, this means that the constant function 1 can be computed by geometric recursion. So here I will not explain what bk and ck are, but they're just explicit functions of 3 variables. I think you just fleshed them out yesterday. But you see, this is completely different from Mirzaani's identity. It's again, an identity for the constant function 1, but on a different space. And the length here of curves, they are measured with respect to a fixed embedded metric Ripon graph. So there's no hyperbolic geometry involved here. But the point is that if you take this combinatorial Mirzaani identity and you use this combinatorial Wolpert formula, you can integrate the constant function 1 against the Kontsevich volume form, and you can get a topological recursion for these Kontsevich volumes. And in this way, we're able to get a geometric proof of Witten conjecture or Kontsevich theorem. So what I want to tell you now is that, well, basically what we can do is the same thing we did before, right? So we can try and again count multicurves in this combinatorial world. So the definition here again is the same, but it's different. I'm considering the same type of counting, but on a different space, this combinatorial moduli space. So the difference here is that I'm counting multicurves with respect to another length function. But again, I can consider this function and it descends to the moduli space, the combinatorial one, and I can integrate it against the Kontsevich volume form. And using exactly the same argument as before, we were able to show that the Laplace transform with respect to this cutoff variable t, it's computed by geometric recursion. And if you also integrate this against the Kontsevich form, this average number of combinatorial multicurves is computed by topological recursion and as a sum over stable graphs. So again, what we can do is express the topological recursion here in terms of the Chekhov and Arthur-Danton formalism, and you basically get the same spectral curve except for the function y. And you can see here that instead of having the sine function, we get just z, which is exactly the one appearing in the Airy curve that I think Alba mentioned yesterday. So this average number of multicurves, they're different, but very similar because, well, the problem is very similar. And again, we can use topological recursion to compute this, and here are some examples. You can see that these are much easier exactly because you don't have all these non-homogeneous contributions that also appear in the Val-Peterson volumes. Okay, so the point of this is that we can compute this average number of multicurves in both the hyperbolic and combinatorial world. But, well, this is an interesting problem by itself, but why should we care? And the point is that, well, there's a connection with another area of mathematics, and is what I want to talk about now. So let me consider this moduli space of quadratic differentials. So if I fix G and N, I want to consider this moduli space parameterizing some Riemann surfaces of a fixed genus G, and meromorphic quadratic differentials where you have n simple poles and just simple zeros that are forced to be in this number here. So the result I want to mention is that this moduli space has a measure, a well-defined measure, and also a notion of volume that is called the Masur-Veech volume, and this volume is finite. So this is a result by Masur and Veech from the 80s. if you know a bit more about Masur-Veech volumes, here I'm just considering the Masur-Veech volume of the principal stratum. But the connection with what I said before, it's a result by Mirzakhani. So what she was able to prove is that the asymptotic number of multicurves gives exactly the Masur-Veech volumes. So in other words, if you take these Masur-Veech volumes up to a certain combinatorial constant that I don't care, is equal to the limit when t goes to infinity of this average number of multicurves. So remember that t is the cutoff parameter. So when you send it to infinity and you normalize it properly, what you get is these Masur-Veech volumes. So this is one other reason why you should care about this counting of multicurves. So here, this result was just in this hyperbolic setting, right? And so what we were able to prove is that this asymptotic number of hyperbolic multicurves is exactly the same as the number of the asymptotic count in the combinatorial setting. So we were able to prove this relation here. And well, if you take this result together with this result and what I told you before, a corollary is that these Masur-Veech volumes can be computed by actually two different topological recursions, the one in this combinatorial setting and the one in the hyperbolic setting. And they're also given by a certain sum over stable graphs. So again, this sum over stable graph result was also kind of known by Mirzakhani and was also proved recently by Delacroix, Gujat, Zograf, and Zorich using different methods. So let me see how much time I have. Okay, I'm almost done. So to finish the talk, let me just mention a couple. One other approach you can take to compute these Masur-Veech volumes. So this was done by Chen, Müller, and Sauvaget, and the idea is that, well, you can take directly the moduli space of quadratic differentials and try to compactify and express the Masur-Veech volume, sorry, the Masur-Veech form as a top form on the moduli space. And so using algebraic geometry, basically, Chen, Müller, and Sauvaget, they were able to prove that these Masur-Veech volumes of the moduli space, of the principal stratum of the moduli space of quadratic differentials, can be expressed as the intersection of a certain homology class, which is the Segre class of this compactified moduli space of quadratic differentials up to a certain combinatorial factor. And so this S of Q bar is actually, it's a Kyoto class, as Danilo described in his talk. So you can use Kyoto's formula to actually represent it as a certain combination of Hodge integrals. But exactly from the fact that this class is just a Segre class, sorry, it's just a Kyoto class, we were able to prove that there exists actually a third topological recursion computing Masur-Veech volumes, and it's the one given by this spectral curve. So this spectral curve is actually computing the intersection of this Segre class with psi classes. And so, yeah, what you can get from this is that there are actually three topological recursions computing Masur-Veech volumes. Two of them are computing counting of multicurves, and one it's computing this Segre class intersected with psi classes. And I also want to mention that using this result of Chen, Müller, and Sauvaget, Kazarian, Yang, Zager, and Zhang were able to prove a different recursion for Masur-Veech volumes that is actually more efficient than the three that we have. And yeah, I think this is a really cool result if you like integrable hierarchies. I really recommend to read these papers. They're they are a really nice application of integrable systems to this enumerative problem. So let me finish with just a couple of open questions. So the first one is, well, can we give a direct geometric proof of the fact that the Masur-Veech volumes are equal to the asymptotic number of combinatorial multicurves? So we know that this result is true, but we know it because we were able to compare this asymptotic to the hyperbolic one, and then using Mertehani's result. But is there a direct geometric proof of this? And a second question is, well, on this moduli space, the combinatorial one, there's an integral structure, and the same is true for the moduli space of quadratic differentials. Is there a relation between the two? And also, is there a relation between lower strata of this moduli space and lower strata of the moduli space of quadratic differentials? And I think that both of these questions can be answered using certain results of Bertola and Korotkin, where they considered this moduli space, the combinatorial one, and they described some period coordinates in this setting. So I think that combining our results to their results, we can maybe answer these two questions. And the last question is, well, can we generalize this to the moduli space of super Riemann surfaces? And yeah, thanks a lot.
Okay, so let's thanks Alessandro. Maybe one or two short questions.
Sorry, I have a question.
Yes, Natalie, please.
Would you tell us what is special about this combinatorial Teichmüller space, about this particular definition that you have there that you make it like kind of a special?
I wouldn't say it's special. I mean, it's somehow a different combinatorial, a different model for the Teichmüller space. Mm-hmm. And when you question about the mapping class group, it's a different model for the moduli space of curves. And well, if you want, what is special is that it has its own geometry. So it has a symplectic structure, which is the Kontsevich one. And you can use the geometry there to obtain some information about the moduli space or vice versa. So basically, if you want everything you can do in Teichmüller theory, you can also do that in that specific case, and it will give you similar results but different. For instance, one thing you can do is give a geometric proof of Witten's conjecture, just using this combinatorial moduli space.
Is there any motivation from the algebraic point of view somehow by choosing this one, not another? I mean, because okay, Teichmüller space is good, but then you have this combinatorial. Why not another thing, another type of that? Is there any like algebraic motivation behind this?
Well, so if you just look at the symplectic structure, I would say that the ordinary Teichmüller space, it captures the geometry of kappa 1 from the algebraic point of view, while this combinatorial one, it's just psi classes. So I don't know, I wouldn't say there's anything special about this. It's just another model that you can consider.
Okay, but you are at the same place, so probably you can discuss it later. Okay, so let's thank Alessandro again.